Today I will give you a brief overview of some of the most important radiative processes in astrophysics. As an overview, I can say that we can roughly divide the processes, the radiative processes, in thermal processes and non-thermal processes. The thermal processes have origin which is related to the thermal motion of electric charges, atoms and molecules. As an example, we have the blackbody radiation and the Bremsstrahlung or free free-radiation. The most important examples in astrophysics of non-thermal processes are instead processes like synchrotron emission or the inverse Compton emission. It can be very complicated, but actually most of these processes come from simple principles of electrodynamics. If we go to the Maxwell equation, the classical Maxwell equations, we know that in classical electrodynamics, the electric field and the magnetic field are related to the electric charges and to the electric current through the four Maxwell equations that you can recognize here to be the Coulomb law, which relates the electric field to the presence of an electric charge, the non-existence of magnetic monopoles, the induction law, the Faraday law, and the Ampere's law. These are the classical Maxwell equations that you should know very well. However, these are four equations, and it is simpler to solve other equations instead. We can use some property of the electric field and of the magnetic field. For example, since the magnetic field is divergence free, we can express it in terms of a vector potential, a vector called A, and we see how the Faraday law is modified by the use of this potential vector. It follows that the electric field can be written in terms of this potential vector and of a scalar vector phi. Okay? So we have introduced one scalar quantity, which is the scalar potential, and one vector quantity, which is the vector potential. And we prefer to work with A and phi instead than with E and B. It is easy indeed to show that the Maxwell equations will get a much less complicated form. First of all, notice that Maxwell equations are invariant under a gauge transformation in which the vector potential and the scalar potential are transformed with the addition or subtraction of derivatives of another scalar quantity or vector quantity. So, since Maxwell equations are invariant for this gauge transformation, we choose conveniently the so-called Lorentz gauge, in which the two vectors, the potential vector and the scalar vector, are related by this equation. Okay. It is easy to show that the Maxwell equations are invariant under a gauge transformation of the two potentials. Gauge transformation is represented here. So this allows to use conveniently this degree of freedom, and we can choose the Lorentz gauge, which is this relation between the two potentials. So, in terms of the electromagnetic potentials, we can rewrite the Maxwell equation, and using the Lorentz gauge, we see that the scalar potential and the vector potential obey two wave equations. So basically, we reduced the four Maxwell equations on E and B to two wave equations for the electromagnetic potentials A and phi. Which is the solution, the general solution of this wave equation? General solution is expressed in terms of the integral over space and time of a green function. The green function has here a special meaning because it has the role of selecting the time variable of the integrand. We can notice that from the mathematical point of view, the effect of a distant source on an observer depends on the source behavior in the past or in the future, in the sense that here in the green function we could in principle select the plus sign or the minus sign. Mathematically this is allowed. However, you know that the advanced solution is unphysical, and this is why we will use from now on only the retarded solution, which means that the values of the electromagnetic field at a given time, at a given point of the space, will depend on the status of the electric charge and of the electric current at a previous time, at a previous position. And this is due to the fact that light needs a finite time to propagate from the position of the electric charge to the position of the observer. So the introduction of the retarded time in these solutions is due to the fact that the speed of light is finite, and the speed of light is the speed at which the electromagnetic signal will propagate. So, using the retarded potentials, we see that the solution of the wave equations can be written in this way. And you see that it is expressed in terms of a retarded time. You indeed notice that x minus x prime divided by c is exactly the time needed for the light to propagate from a position to the observer. So, what happens if we consider a moving charged particle? For a moving particle, this leads to the so-called linear Vickers potentials, A and phi, which are given by these functions of the electric charge and of the electric current, evaluated at the retarded time. Okay, so the potentials at x and t depend on the status of the charge and of the current at the retarded time. Okay, the retarded time can be easily found if you know the trajectory of the particle. Okay, here you see the particle moving along a trajectory, the position of an observer x and t, and you see that the value of the potential here depends on the status on the charge at t prime, which is indeed the retarded time. What do we do now with A and phi, with these potentials? We go back to our Maxwell equation and we calculate finally the electric field and the magnetic field. Okay. What is extremely important here to notice is that the electric field as well as the magnetic field can be written as the sum of two terms. One is velocity field. It's a term which only depends on the velocity of the electric charge. And the second term, which is proportional, which depends on the acceleration of the particle, the so-called acceleration field, is what gives rise to the propagation of electromagnetic waves. So we see that the velocity field is falling off as the inverse of the square of the distance between the particle and the observer. And the acceleration field, on the contrary, is falling off just as the inverse of the distance. If we go in a region which is far from the particle, from the moving electric charge, we see that the radiative field is dominating over the velocity field. And this is the reason why we will restrict ourselves for our astrophysical applications to the radiative part, to the acceleration field. Okay. Notice also that the magnetic field and the electric field, together with the direction of propagation of the radiation, form an orthogonal triad. So, in the non-relativistic limit, the electric field and the magnetic field are related by this simple equation. How can we calculate the energy which is carried by the corresponding electromagnetic wave? we can make use of the Poynting vector, the vector S, whose amplitude is proportional to the square modulus of the electric field or of the magnetic field. And using the Poynting theorem and calculating the Poynting vector, we can derive the value of the power that this moving charge is emitting per unit solid angle. So the energy emitted per unit time per unit solid angle. The elementary form of this power is given by this differential Larmor formula. If we go to integrate it over all the solid angles, so if we calculate the energy which is emitted by the electric charge over all the space, we obtain the Larmor formula, which is the integral version of this one. And we notice that the total power emitted is proportional to the square of the electric charge, and most importantly is proportional to the square of its acceleration. So the message to take home now is that any particle which is accelerate radiates power, emits energy, okay? So accelerated charges emit energy. And this is very important because it is one of the basic mechanisms by which astrophysical sources are able to emit radiation. Einstein identified three basic processes in the interaction between matter and radiation. One is the process of absorption. When light is propagating through a volume of matter, they interact, and the matter can absorb the incident photon. However, the matter interacting with radiation can also emit spontaneously a photon, or the incident radiation can generate the so-called spontaneous emission of radiation, which is the basic principle of lasers and masers, for example. There is another process, which is the scattering, in which you do not have any absorption or emission, but just the deflection of an incident photon, which can arise from the scattering with different energy, and so with different frequency with respect to the initial status. When the light propagates into a medium, we can say that the medium is optically thin when all the radiation which is internally generated is free to escape from the emitting region without any further interaction. On the contrary, we say that the medium is optically thick when the radiation which propagates in the matter can only travel a short distance within the medium before being absorbed again. Of course, the shape of an initial spectrum of radiation which is propagating through matter will be modified by processes like emission and absorption. The shape of the final spectrum can be obtained by the balance between emission and absorption processes. When a region is optically thick, this amounts to constraining the spectrum to be not more efficient than a black body, and we will see some consequences of this. As I mentioned at the beginning, one of the most important emission processes of radiation lies in the black body radiation. You should consider that any object which has a temperature above the absolute zero emits energy in the form of electromagnetic radiation. What is a black body? A black body is an hypothetical object which is considered like a perfect absorber and a perfect emitter. So a body which is able to absorb all the radiation falling in it without any reflection or transmission of light. Technically, the black body spectrum is describing a spectrum of radiation which is in thermodynamical equilibrium. The spectrum of the black body has very important properties. One of these is that the shape of the spectrum is described by this function, the so-called Planck function, which depends only on the temperature of this radiation in thermodynamical equilibrium. And here in this plot you can see how the Planck function with increasing temperatures keeps the same shape. The only difference is in the amplitude of the spectrum and in the position of the peak, which is translated to our higher frequencies for higher temperatures. We can also notice that the Planck spectrum presents two well-defined regions, the Rayleigh-Jeans region corresponding to low frequencies, h nu much smaller than kT, where k is the Boltzmann constant and T is the black body temperature, and the V region, in which you see that the spectrum is going down very steeply. Which are the astrophysical examples of black body emitters? Although a star cannot be considered exactly a black body, using a black body spectrum for the spectrum of a star is, under certain approximation, a good assumption. And the surface temperature of a star can often be deduced from the wavelength of the peak in its spectrum. But without any doubt, the most perfect example of black body spectrum that we found in nature is the spectrum of the cosmic microwave background radiation, which is the relic radiation from the Big Bang. There was a time when the universe was very hot and dense, in which the radiation was coupled with matter, and so it was in thermal equilibrium with matter. After the decoupling, this radiation was free to propagate without any other interaction with matter, and so the shape of the initial spectrum was preserved until the present time, and it is the spectrum of radiation in thermodynamical equilibrium with matter. So it is a perfect black body. This black body radiation was discovered in the 60s, and it is a remarkable fit to a black body with a temperature of 2.725 Kelvin. If you compare the theoretical curve of a black body spectrum with the data collected by the satellite COBE, you see this remarkable fit. Okay? So also here you can see a map of the cosmic microwave background radiation. The fact that the relic radiation from a Big Bang is a perfect black body, which was also confirmed by further experiments like Planck and WMAP, can be interpreted as the proof of the Big Bang, as the evidence that the universe has been expanding and cooling for more than 13 billion years. Actually, the most recent measurements of it discovered very tiny temperature fluctuation in the early universe. These fluctuations that you can see, for example, in this map, are actually the seeds of the large-scale structure that we observe today. There is another mechanism of thermal emission in matter. If you remember, I said that any accelerated charge will emit radiation, described by the Larmor formula. Well, in the Bremsstrahlung, also said free radiation, is the radiation which is emitted by a charged particle which is accelerated in the Coulomb field of another charge. It is also called free radiation because the initial charge is not bound to an atom before the interaction and after the interaction. The detailed treatment of the Bremsstrahlung radiation requires quantum electrodynamics. However, we can get important qualitative results even without using the full quantum formalism. We know that in astrophysical plasma, the electrons are accelerated by interaction with the positive charged ions. And this is the dominant mechanism of emission in a plasma. And it is also a very important mechanism by which plasma can cool, can reduce its temperature. An example of Bremsstrahlung radiation in astrophysics is given by the radio emission from H2 regions, which are ionized regions around massive newborn stars, typically OB stars, which are emitting a large amount of ultraviolet radiation and which are able to ionize a spherical region around them. In this region, you have free electrons which interact with positively charged ions, and this gives rise to Bremsstrahlung emission, which is detectable. Another example of Bremsstrahlung radiation in astrophysics consists in the radio emission from ionized winds and jets in galaxies. And also the X-ray emission from clusters of galaxies is a typical example of Bremsstrahlung radiation. How do you calculate exactly the spectrum of Bremsstrahlung? You should consider a specific impact parameter, specific minimal distance between the positively charged ion and the electron, and you should know the velocity, the average velocity of the electric charge. Apply the Larmor formula. The intensity spectrum of the emitted radiation can be calculated using the Fourier transform. If you have instead a distribution of velocities and distribution of impact parameters, you have to integrate over B, the impact parameter, and over the velocities of these particles. For example, if you assume that the plasma is in thermal equilibrium, the particles will have a Maxwellian distribution of velocities, so you will have to integrate over all this distribution. What happens at the end is that you will find a result which has to be corrected by the quantum effects. As I said, we are not treating in detail the quantum effects because the classical physics can well describe the Bremsstrahlung emission, but you have to introduce a corrective factor at the end when you have your result, which includes all the possible quantum mechanical corrections. This factor is the so-called Gaunt factor for free emission. The Gaunt factor is again a function of the temperature of the particle distribution, of the charge of the ions, and of the frequency of the spectrum. At the end, you will calculate the emissivity for Bremsstrahlung. So the power which is emitted per unit time, per unit frequency, by the unit volume of your plasma. Okay, here you see the expression of the emissivity in watt per cube meter per hertz. And you see that it depends on all the parameters, which is the typical shape of the Bremsstrahlung spectrum. Here you have a flat region, which is almost flat actually, because the presence of the Gaunt factor is inducing here a very small steepening. And then you have a thermal cutoff, because every time you have a Maxwellian distribution of velocities, you also have a maximum of the kinetic energy of the particles, and so a maximum value of the energy of the photon, which can be produced by this acceleration of the electrons. To explain this part of the spectrum, you have to calculate also the contribution by absorption of radiation, which I anticipated. The fraction of intensity of radiation which is lost per unit distance as the light propagates in the medium is given by the Kirchhoff law, which relates the emission coefficient and the absorption coefficient to the Planck function. Okay? And this is also the relation which allows to define the optical depth for a medium. If the plasma is optically thin, you see that the spectrum is approximately flat until the turnover, which is here, and here the spectrum is going rapidly down because of Bremsstrahlung self-absorption, which means that the medium is absorbing the Bremsstrahlung radiation which was produced by itself. So this is the typical shape of Bremsstrahlung spectrum. Notice that at low frequencies the spectrum is proportional to the square of the frequency, so it is a black body-like spectrum corresponding to the region in which the medium is optically thick to radiation. Examples in astrophysics, the H2 regions are a very good example of Bremsstrahlung emission. Here you have an OB star which is photoionizing all the gas surrounding the star, and the resulting plasma has a typical temperature of around 10 to the 4 Kelvin. For example, you see this Bremsstrahlung emission in the Orion Nebula, where you have a region of forming stars, or in the Tarantula Nebula. You have the formation of these big OB stars, which is able to ionize all the gas around, which will be emitting Bremsstrahlung radiation. Also in galaxy clusters, you have intra-cluster gas, which has now a higher temperature than H2 regions. Indeed, here the temperature can reach values as high as 10 to the 8 Kelvin, but the atomic density is very low in this case, because we have 10 to the minus 3 electrons per cube centimeter. At such temperatures and at such densities, the primary emission process for this gas is exactly Bremsstrahlung emission. And for example, here you can observe the Hubble cluster observed by the satellite Chandra in the X-ray band. You see here, this is the Bremsstrahlung emission of the cluster. And here you see the cluster observed in the optical band. Also, our own galaxy, the Milky Way, is emitting free radiation. And for example, here you can see a map of the Milky Way emission taken by the Planck satellite. Okay? This region corresponds to our galactic disk, and the intensity, which here is plotted in red, proportional to the intensity of the free radiation emitted by the free electrons in the disk of our own galaxy. Let's go now to non-thermal processes, okay? Until now we were talking about particle moving just because they have thermal energy, because they have a non-zero temperature. And this gives rise to a random motion, and this gives rise to an acceleration. However, there are non-thermal mechanisms which are able to produce an accelerated motion of particles. And the most important we find in our universe is the synchrotron radiation, which is very common in compact objects, but also in galaxies and in clusters. Synchrotron radiation is the radiation which is emitted by an electric charge when it is accelerated by a magnetic field. In the non-relativistic case, so when the velocity of the particle is much smaller than the speed of light, we talk about cyclotron radiation. The common situation in astrophysics is that we deal with relativistic particles, and so we have synchrotron radiation, which is the relativistic generalization of the cyclotron radiation. And to calculate the power which is emitted by a charge accelerated by a magnetic field, we can just make use of our Larmor formula, which relates the power emitted to the acceleration of the particle. How do you find the acceleration of a particle in a magnetic field? By just using the equation of motion, or better, their relativistic form. Indeed, we introduce the gamma factor and the beta factor, which is the ratio between the velocity of the charge and the speed of light. We calculate the components of the velocity of the particle parallel to the line of forces of the magnetic field and perpendicular to it. And we see that the magnetic field is inducing in the particle an acceleration which is only perpendicular to the magnetic field itself. So you do not have any acceleration parallel to the line of force of the magnetic field. You only have an acceleration perpendicular, which gives rise to a circular motion of the charge, or if you have a non-zero component of the parallel velocity, an helicoidal motion of the particle. Okay. For this circular motion, you can easily calculate the radius, the Larmor radius, and the typical gyration frequency, the Larmor frequency. Okay, so if these are the magnetic line force, you see that the electron is typically spiraling around them and emitting synchrotron radiation in the instantaneous direction of motion. Here you can also see the typical shape of the spectrum of synchrotron radiation in the case in which you have a large population of particles. A large population of particles is radiating over a very large range of frequencies. Okay, so when you have a distribution of particles, in general, you will have to average over the pitch angles of these particles, which is the angle between the direction of motion of the particle and the direction of the magnetic lines of force. And what you find is that the power emitted by synchrotron radiation from a population of electric charges is given by this expression, which depends on the average velocity of the particles. Here we assume that all the electrons have the same velocity, and it is proportional to the Thomson section of the electron and to the energy density of the magnetic field. So, for example, here you have a spiraling electric charge which is moving around the line of force of a magnetic field, and it is emitting exactly in this direction. So the emission is very beamed, and the aperture of this cone of emission is inversely proportional to the gamma factor. Also, our own galaxy, the Milky Way, is emitting synchrotron radiation because we have a magnetic field in which electric charge moves. And so, for example, here you have an all-sky view of the synchrotron emission as measured by the Planck satellite. The colors here represent the intensity of the synchrotron radiation, and the pattern you can see indicates the orientation of the magnetic field, which is projected on the plane of the sky and which is orthogonal to the observed polarization. So in our galaxy, if you look at the disk of the galaxy, you have not only free emission, but you also have a synchrotron emission thanks to the galactic magnetic field. The last radiative process that I would like to describe is not an emission process, but it's actually a scattering process. And I'm referring to the Thomson scattering. Thomson scattering is the mechanism by which you have scattered radiation from a free electron in response to a linearly polarized electromagnetic wave. If you calculate the force acting on the charge, you find that the electron will start to oscillate under the action of the incident wave, because you associate an electric field to the wave. So the electron will start to oscillate and will scatter the radiation in any direction. So you have an oscillating dipole. Using the Larmor formula on this dipole, you can calculate the pattern of the emitted radiation and the total power emitted in Thomson scattering. Notice that this is an elastic scattering, which means that the frequency of the incident wave is the same as the frequency of the scattered wave. This can only happen when the energy of the incoming photon is negligible with respect to the rest energy of the scatterer, which is the electron in this case. Okay? But in cosmology, in astrophysics, the Thomson scattering is not the most typical situation. What we have instead is the Compton scattering, which happens when the energy of the incoming photon is comparable to the energy of the electron. The Compton scattering is indeed the quantum mechanic analog of Thomson scattering. Compton scattering results in two different processes. The direct scattering, in which the photons lose energy when they interact with the electron, and the inverse Compton scattering, in which, on the contrary, the photons are gaining energy in the interaction with the electron. And so in astrophysics, the Compton scattering is the process which is associated, for example, to interstellar reddening, the reddening of radiation from a distant source, which is proportional to the distance that the light will travel. The longer wavelength, for example, the red light, are not scattered as easily as the shorter wavelengths. And so the radiation which is passing through interstellar dust will be reddened by Compton scattering. And of course, this will change the expected spectrum of an astrophysical source. There will be a distortion of the spectrum. And also, for example, broadening of the spectral lines. Another example of Compton scattering in astrophysics is found in the AGN. AGN are active galactic nuclei. They are very bright in the X-ray radiation, but there is an excess of X-ray emission, in particular the soft component of X-ray, which cannot be explained from Bremsstrahlung. And we think that this can be instead explained by Compton scattering. Inverse Compton scattering is also thought to account for the gamma ray emission in some quasars. It is observed in the jets and in the extended regions of radio galaxies. And in these cases, the Compton scattering is considered more important than synchrotron radiation as an energy loss mechanism for electrons. Coming back to the CMB, there is another effect of the inverse Compton scattering which is observable, and it is the Sunyaev-Zeldovich effect. The Sunyaev-Zeldovich effect is the distortion of the CMB spectrum. You know that the CMB spectrum is an almost perfect blackbody, and the Sunyaev-Zeldovich effect is the distortion of this spectrum through inverse Compton scattering, which is due by the high energy electrons in the galaxy clusters. So when the radiation from the Big Bang is crossing a galaxy cluster, the low energy photons from the CMB interact with the high energy electrons of the intracluster plasma, and they receive a boost of energy during this collision. So the low energy photons of the CMB are shifted to much higher energies. As a consequence, the CMB spectrum will have a distortion in correspondence to the position of galaxy clusters. You see here that the initial Planckian function is shifted toward higher frequencies. And here you have the scheme of how a CMB photon is crossing an overdensity corresponding to the hot gas in a galaxy cluster, and it is blue shifted. Using the Sunyaev-Zeldovich effect, many dense clusters of galaxies have been observed.